As always, let me know if you have any questions. Feel free to unmute yourself and speak up, or send me a message in the text thread. Or if you're watching this video later, feel free to message me anytime, night or day. So we've been talking about, in chapter 21 here, carboxylic acid and carboxylic acid derivatives. And we said of the carboxylic acid derivatives that include amides, esters, anhydrides, and acid halides. The halides, especially the acid chlorides, are especially electrophilic. They're strong electrophiles, both kinetically and thermodynamically. We went into a lot of detail on that last time. Thermodynamically, it's mainly because they produce a chloride leaving group that's very stable, favoring the product side. Kinetically and thermodynamically, there are also in an acid chloride a very large partial positive here that's not stabilized well by the chloride's lone pair due to ineffective orbital overlap. So both through induction and resonance with the oxygen, the carbon holds a large partial positive. The chloride's not very sterically hindering, so it's easy for nucleophiles to attack there. And we showed how nucleophiles can come in there, push electrons up. When they swing back down, it pushes out the chloride. So today we're going to talk about how to make acid chlorides, since they are so good as electrophiles. And then we're going to look at a variety of nucleophiles that can actually come in here to the carbonyl carbon and replace the chloride and the synthetic utility associated with that. So the main way to make an acid chloride, there's more than one way. The textbook focuses on one specifically. I think it's a bit more traditional. Is to use thionyl chloride, which is SOCl2. So thionyl chloride has a sulfur atom with a huge amount of partial positive. And here, if we look at the sulfur atom, even before the oxygen attacks, there's a resonance contributor here where the sulfur has a single bond and a positive charge. So this is actually the major contributor because of the ineffective orbital overlap between the sulfur and the oxygen, given that they're in different energy levels, or their p orbitals are in different energy levels. So the fact that this is a major contributor to the resonance means the sulfur carries a very large amount of positive. So that is a very electrophilic sulfur. And this oxygen here has a large partial negative. We've seen this oxygen of a carbonyl picking up protons in the past. So this isn't so different. This is a Lewis acid instead of a Bronsted acid. So instead of picking up a proton, it picks up and attracts to a different positively charged atom, namely the sulfur. So when that comes in there and forms this new bond, these electrons here can swing up, and this oxygen can swing in. So there's resonance here. These electrons can also swing back out. So the swinging in and swinging back out is an example of resonance. If these swing out, it gives a positive on the carbon. So these can also swing in here. Should be an extra lone pair here. Those can also swing in, and so that positive actually exists on both these oxygens as well as on the carbon. So that really helps to stabilize that intermediate. So here's another example that goes against this general rule we've been saying, where generally we don't see two neutral compounds reacting to form a substance with multiple formal charges. This oxygen's formal charge is stabilized by resonance with the sulfur, and this oxygen's positive charge is stabilized by resonance over both the oxygens and the carbons. So these are relatively stable formal charges here, which is mainly what allows this process to occur. It can simply go back. So we could imagine the oxygen shifting these electrons back in and pushing out this leaving group and going back. Right? So this is definitely an equilibrium step. And this intermediate's not super stable, so it might go back and forth and back and forth. But then occasionally, if the electrons swing out and push out a chloride leaving group, that's a great leaving group as well. So that helps the process go forward. So after that occurs, the next intermediate here, shown right here, the chloride can then act as a base to pick off this proton to produce a Newton, another intermediate that's neutral. However, we know chlorides are terrible bases because their conjugate acids are very strong with pKa's on the order of -7. Right, so that's a really strong acid. So that's relatively unstable, and forming such an unstable substance from a thermodynamic perspective makes the products less stable and it makes the process less product favored. So typically when this reaction is done, in addition to adding thionyl chloride, usually pyridine is also added, and the pyridine is used as a base specifically to pick off this proton. So since this is a carboxylic acid, it's a weak acid, but still acidic. Weak base, weak acid, they probably will react together right away. So you can imagine the pyridine picking off this proton and this electron pair staying behind on that oxygen, and then attacking the sulfur to form this intermediate, but the proton wouldn't be there. And so that would avoid one of these formal charges and make the first intermediate more likely to occur as well. You could also show in this reaction, you could also show the pyridine picking off the proton at this stage as well. So either picking off the proton from the carboxylic acid before it attacks the thionyl chloride or after. Probably some molecules have their proton picked off before and some after, so either of those options are reasonable. But pyridine would probably be picking off this proton rather than chloride, assuming that you're following a procedure that involves a weak base like pyridine, and most do. So that's typically what we would see. And once we form this intermediate, we can think of this group here in gray as a very good leaving group. And so what would happen next to that structure, which is right here, is a chloride would attack the carbonyl carbon. Right? So just it's a slightly different perspective, but instead of picking off a proton, the chloride would then be free to attack this carbonyl carbon and shift these electrons up. So after that attack, shifting those electrons up, we get another intermediate. And now when the electrons swing back down, it could push out the chloride and go back, or it could push out this excellent leaving group. And what makes this such a great leaving group is once it forms, the electrons can swing in and push out another chloride, which is especially stable, and the SO2 that's formed is a gas. And so it leaves the reaction and is unavailable to collide with the chloride and then go back. So this last step is not really reversible. The last step is really kind of what drives us forward, producing a gas that evolves from the reaction. And by Le Chatelier's principle, removing one of the products of the reaction helps to shift the entire equilibrium toward the product side. So usually we use a non-nucleophilic base like pyridine, right? That's important that the base be non-nucleophilic. We can't use a base that could also act as a nucleophile, otherwise it'll start attacking here and pushing out the chloride, and we're getting ahead of ourselves in terms of what we want to use this acid chloride for synthetically. So if we're just trying to form the acid chloride, we want our base to be non-nucleophilic. So the pyridine, it can pick up a proton and stabilize the positive charge, but if it comes into a carbon and forms a bond to a carbonyl carbon or any other carbon, its positive charge will make it a pretty good leaving group. So it would probably just end up leaving that structure. So its purpose is to act as a base and specifically pick off the carboxylic acid proton. Removing that proton makes the carboxylic acid a better nucleophile, makes it more able to attack the thionyl chloride, and then it will go through more stable intermediates during the mechanism. So that's how we make an acid chloride. And also, what are some of the reactions that acid chlorides can undergo? Well, one is a reaction with water. Water is a weak but decent nucleophile. And we talked about this last time. We said how the acid chloride is such a really strong electrophile. It's got a great leaving group. It's got a very large partial positive there. So here's another example where two neutral species can react to produce an intermediate with two formal charges. So if you're looking at drawing these mechanisms while you practice for the exam, you might want to categorize them so you can keep straight in your mind which mechanisms are able to go through intermediates with two formal charges on the same structure and which are not. It really depends on how unstable the reactants are, especially if we have one reactant that is quite reactive and has a large partial charge, then it'd be easier, that starts off higher in energy, so it's easier to get to a relatively high energy intermediate that would resolve. So once this intermediate forms, the electrons can swing back in and push the water out, so it can definitely go back, or they could swing back in and push out the chloride, which would go forward, and then another water molecule, since we're using water as a reactant, we'd probably use it in large excess to shift this equilibrium toward the product side, can be used to pick off that proton. You could also add a weak base like pyridine to pick off that proton. But that forms a carboxylic acid. So this is if you want to convert the acid chloride into a carboxylic acid, you just treat it with water. And what this means is, if you've made an acid chloride and your goal is to react it with something to make an ester or an anhydride or an amide or any of the other functional groups we're going to see that can be made from this a little bit later today, you have to protect it from water because it can react with water to produce a carboxylic acid. If you want to make a carboxylic acid, react it with water. If you want to keep it as an acid chloride so some other nucleophile other than water can attack it and replace the chloride leaving group, you can't have a bunch of water around. So that means you have to store it in a dry atmosphere. You want to probably set the reaction up after flame drying the flask and using a nitrogen atmosphere so moisture can be excluded from the reaction. And the acid chloride can be saved for reacting with the nucleophile of your choice. So here's an example of a reaction you might want to do. There are lots of situations where you might want to synthesize an ester. An ester has a CO double bond with an oxygen. It's like a carboxylic acid, but there's an R group where the proton would be. So we have an R group and then this grouping of oxygen and carbons and then another R group to make an ester. So if one R group is already present on the acid chloride you've made, which you would again make from typically the carboxylic acid that would usually be available in the presence of thionyl chloride and pyridine to make the acid chloride, then all you have to do really is add an alcohol and another shot of pyridine, which again is a weak non-nucleophilic base, to facilitate this reaction. So what happens in this mechanism is the pyridine is not going to pick off this proton to begin with. Because if the pyridine picks off this proton and these electrons stay behind on the oxygen, that's going to create a negative formal charge on the oxygen that's not stabilized by resonance or induction or really much of anything on such a small atom. That's not going to be likely to occur. The acid-base equilibrium would greatly favor the proton staying on the oxygen versus going to the nitrogen. So this is another example, and this is a common theme. When you have an acid chloride, that even a weak nucleophile can attack there because there's such a large quantity of partial positive to push electrons up, and that commonly gives an intermediate that has two formal charges on the same structure. We still have a proton here, So this oxygen is positive, right? Two formal charges there. So then the oxygen's electrons could swing back down. It could push this oxygen back out and go back, or it could push out the chloride, since that's also an excellent leaving group. So if the chloride leaves, then you'd have reformed the CO double bond, and you're almost at the ester. You just have to remove this proton, and that's what the pyridine is for. So now that the oxygen is positively charged, the pyridine can pick up that proton, and it would be reasonable to show that occurring either here before the chloride leaves, or since this is intramolecular, it's probably more likely to occur first, but I wouldn't be that strict about that order in which those steps occur. The pyridine could also pick off this proton after the chloride leaves, and that would give the product. And instead of forming HCl, because the chloride doesn't have to pick off the proton, the pyridine is a much better base than a Cl minus. So having the pyridine pick up that proton, instead of producing HCl, it produces pyridinium. And that's much more stable with a positive than HCl is in terms of the pKa's. HCl's pKa is around -7. This pKa is probably, I think, around 4 or 5. I think it's close to 5. So this is much more stable than the HCl as a final product there, in addition to the ester that you form. And since this is charged, once you form the ester, and you probably would end up setting up an extraction in a separatory funnel, this charged substance would end up primarily going into the aqueous layer, separating from the desired ester product that you've made, which would be in the low polarity layer, given that these R groups are generally not highly polar groups. So that's one option. You can use an acid chloride to make an ester. Another option, you can use an acid chloride to make an amide or amide. And depending on how many hydrogens or R groups are on the nitrogen, when it attacks, you can make an amide that has an NH2 next to the CO double bond, or one R group on that, or 2. Right? So we're not going to use a tertiary amine here. We're going to use ammonia, a primary amine, or a secondary amine. Right? Because if I use a tertiary amine would have 3 R groups. And if that attacks and forms a new bond to the carbon with 3 R groups, it can never lose a proton in order to balance its formal charge, and so it'll always be somewhat unstable. So tertiary amines in other amines like pyridine that don't have any protons on the nitrogen aren't really good nucleophiles, so we wouldn't be able to have them attack here. They would just get pushed back out as a leaving group. So we have any one of these nitrogens could come in here, push electrons up, and go through the mechanism to produce this amide. So we need 2 equivalents, meaning for every 1 mole of acid chloride, we need 2 moles of the amine. And that's true in each of these cases. So let's take a look at the mechanism to explain why that is. So what's going to happen here, whichever ammonia, primary or secondary amine we use, it's going to start off by attacking and pushing electrons up. And again, because there's so much partial positive here and a nice partial negative here, and the nitrogen is low enough in electronegativity that it's quite willing to share its pair of electrons to form a new bond. This is another example where we can go through an intermediate that has 2 formal charges at once. So this nitrogen still has 1 R group and 2 protons. That gives it a positive formal charge. So now the most likely next thing to occur probably would be the intramolecular loss of the leaving group. It could also push the nitrogen back out, so that step could definitely be reversible. If the chloride leaves instead, though, as we reform the CO double bond. Now we can see we're almost at the amide. We just have to remove a proton. And that's why we need two equivalents of this. So we're using specifically two because the first one is used up during the nucleophilic attack to form this intermediate, and then the next one is used up to pick up a proton to make the nitrogen neutral. And so as a byproduct, we would form the conjugate acid of that weak base. And so that mechanism you can apply to any one of these three reactions. So we can use acid chlorides to make an ester or an amide. Acid chlorides can also be attacked by LAH, which is definitely my favorite reducing agent because it's so strong. And it delivers a hydride or a hydrogen with a pair of electrons. So this negative, as we've been saying, on LAH is very unstable, and it will pretty much react with any electrophile. And here we have a really strong electrophile with a very large partial positive. So this reaction should be very fast and very product favored and not reversible, right? We're not going to have the oxygen swing electrons back in and push out a hydride. That's not a good leaving group. So this reaction will not go back. The hydride will be delivered, pushing electrons up to produce a negative on the oxygen. This negative is way more stable than the negative on the much less electronegative aluminum. But we still have a great leaving group, so the oxygen would swing electrons back in to balance its charge, pushing out the chloride. And the chloride then, which is even way more stable with a negative charge, really helps that step to go forward as well. So we wouldn't expect the chloride to come back in there. If it did come back in, it would just be pushed out again. So this equilibrium, again, it could go back and forth, but it would be extremely product favored because of the stability of the chloride versus the oxygen with the negative charge. The issue here, though, is once the acid chloride is converted to the aldehyde after one hydride is delivered there, it's still electrophilic. Not as much, because here the chloride is pulling electrons away, creating even more partial positive, whereas here the hydrogen doesn't do that, so the amount of partial positive is less. But we know LAH is a really strong reducing agent. It's very unstable, and it's capable of delivering a hydride to virtually any carbonyl carbon. So once the aldehyde forms, it's really impossible to prevent the next step from occurring. So if you were to do this in the lab, knowing that you can't stop at the aldehyde, you would probably intentionally use excess LAH so that all of the structures get fully reduced. Another hydride would be delivered, and that would produce this intermediate, which would accumulate in solution until a second step where a protic source is added, right? So again, every time we've seen LAH, we know it's a two-step process. The first step, you add the excess LAH. That gets the reaction to a negatively charged oxygen, which is a lot more stable than the initial negative charge on the LAH itself. And then in a separate step, we add acid, because if we add the acid with the LAH, they'll just react directly. And we want the LAH, obviously, to react with the carbonyl. So this is the second step. The oxygen gets protonated, and we get a primary alcohol. And so it's another way to make a primary alcohol, and this reaction should work quite well, especially if you have the acid chloride. So there is also a method to convert an acid chloride into an aldehyde and not continue reducing that all the way to the primary alcohol. And so we just saw, if I treat this with LAH, it'll convert it to an aldehyde, and then another LAH inevitably can't stop it from reacting, will make the primary alcohol. So this reagent here, which is lithium triterbutoxy aluminum hydride, is like LAH in that it has a hydrogen bonded to an aluminum with a negative charge, and that negative is unstable. So it's very good at delivering that hydride to a carbonyl carbon, which would produce this. But the difference is these terp-butoxy groups are on the aluminum instead of hydrogens. And we know terp-butyl groups are some of the most sterically hindered groups. So what happens here is when this oxygen, when these electrons swing up to this oxygen, it becomes negative. It forms a pretty strong attraction to the aluminum because these terp-butoxy groups on the aluminum are pulling electrons away from it through induction, creating a lot of partial positive there, and the oxygen will form an attraction. So it's kind of almost like an ionic bond attraction. Unless I have an extremely polar solvent, which I don't, when I do this, it's not going to be able to separate those. They'll remain attracted in a close proximity. So what this means is when the oxygen swings the electrons down and pushes the chloride out to make the aldehyde, the aluminum is still there. And its extremely bulky terp-butoxide groups are really blocking space big time. So with one of those already attracted to the oxygen and quite strongly attracted, blocking out a lot of space, it's not really possible for another hydride to come in here and be delivered and react with the aldehyde, because this hydride is on aluminum that has a whole bunch of steric hindrance, and the oxygen is on the aluminum, there's a whole bunch of steric hindrance. All that steric hindrance means that those two molecules can't really form a stable transition state when they collide because of all the steric repulsion. So when the acid chloride receives the first hydride and forms this intermediate, and then the oxygen swings its electrons down and pushes out the chloride to form the aldehyde, its association with the aluminum and the steric hindrance associated with that, and the steric hindrance down here, prevents another hydride from coming in. So this is a reaction that stops at the aldehyde. So now we have another way of making aldehydes. Right? The way we talked about making aldehydes previously is by using PCC and dichloromethane as a solvent to oxidize a primary alcohol to an aldehyde. Well, now we have a way of reducing an acid chloride to an aldehyde. So that gives us a lot more synthetic options for making aldehydes if that's our target compound. So another nucleophile that can attack an acid chloride is a Grignard. Right? So we know in a Grignard reagent, there's a carbon that's sharing electron with magnesium, and the carbon is so much more electronegative than the magnesium. It basically owns those electrons. It creates too much negative for it to really stabilize, so it needs to share those electrons. So we know the Grignard is a very strong nucleophile, and it will attack this carbonyl carbon and push electrons up. But then because the chloride is there, the electrons will swim back down and push out that leaving group, and that produces a ketone. Even though there's a couple relatively sterically hindered R groups here, I don't have that aluminum with like the hugely, massively sterically hindered groups, and generally carbonyl compounds don't have much sterics, so because they're flat. So another Grignard I expect to be able to come in there. So if even if I try to use only 1 mole of Grignard for every 1 acid chloride, when a mole reacts there to produce this ketone, there's a decent chance that another Grignard will attack there just by random collision before it has a chance to collide over here. So since I can't stop the second unit of the Grignard coming in, I would just use excess of the Grignard. By using excess, I can make sure all these steps occur for all the structures and get a pretty high yield of a product that results. So one Grignard comes in, pushes electrons up, they swing back down, push out the chloride, that produces a ketone. Another Grignard would be available to attack there, push electrons up again. That would produce this intermediate, which would accumulate in solution because it's way more stable with the negative than these Grignard reagents are with the large partial negative on a carbon, until a second step where you add an acid to protonate that, right? So we've seen a lot of examples of LAH and a lot of examples of using the Grignard throughout the semester, and hopefully by now you recognize that process is always going to be 2 steps, because the proton that you're using to convert this alkoxide into an alcohol can't be present when the Grignard is present, or it'll just protonate the Grignard. So here's a way to get a tertiary alcohol, specifically a tertiary alcohol in which 2, at least, of the R groups are identical. Right? How do I know these are identical? Well, they both came in from the same Grignard reagent. So if I have an acid chloride, it's got the potential to receive 2 units, 2 R groups, because the first one will push out the chloride and the second one will create an addition across the pi bond. But those 2 groups will be identical because it's not going to be a clean reaction if I use a mixture of different Grignards, because I can't control where each one attacks. So I'd get a complicated mixture of products. So all my Grignards are going to be the same structure. It's going to attack there twice. So 2 of the R groups in the end will be the same. So that's kind of a thing to look for. If I ask you to synthesize a tertiary alcohol and you see 2 of the R groups attached are identical, that's a good sign that this would be a convenient route to go through to synthesize that. So, what if we want to stop the ketone though? Right, so we're saying the first Grignard attacks, electrons to make down, push out the leaving group, and I get a ketone. What if I don't want another R group attacking? What if I'm trying to make a ketone from an acid chloride? Well, the Grignard is too powerful. The Grignard is too unstable and too strong. The magnesium carbon bond is too polar, too much negative on the carbon, and so the carbon will attack at both of these, and I'll end up with the 2 R groups connected there that we said. So instead of using a Grignard, we use some other reagent called a Gilman reagent. The Gilman reagent is also an organometallic compound, meaning there's a carbon bonded to a metal. It's just that the metal is copper here instead of magnesium, right? So we said in the Grignard reaction, the magnesium carbon bond is very polar. The magnesium really needs to get rid of those electrons entirely to make its noble gas configuration, and so they're almost exclusively on the carbon, giving it a negative charge, making it a really strong nucleophile. So it would attack an acid chloride. It would also attack a ketone. But the Gilman reagent, because it includes copper, which is never going to make a noble gas configuration no matter what, and much better at actually attracting electrons a little bit, the copper, I probably shouldn't draw the arrow like that. Let me fix that real quick. Yeah, so the carbon of the R group is still more electronegative than the copper, but the difference isn't so great, right? So the copper is more electronegative than magnesium, and that means this pair of electrons here is more effectively shared. It still shifts more toward the carbon. It still shifts more toward the carbon, so I still have a partial negative and a nice big partial positive. And so it can still rip the electrons away from the carbon and deliver them here to push these electrons up. But once it does that, and that produces a similar intermediate to what we saw with the Grignard reaction. And since there's still a chloride there, the electrons would swing back down and push that chloride out and produce a ketone. But now, if another Gilman reagent collides with the ketone, because the Gilman reagent has 2 R groups, and so does the ketone, there's a lot more sterics. And because the ketone's R groups are donating electron density through induction and hyperconjugation, there's a much smaller partial positive here than there is over here because of the chloride pulling electrons away from that carbon. So what Gilman did here was to kind of fine-tune this reaction. This reagent is fine-tuned to the point where there's enough negative on this carbon and positive on this carbon to cause the nucleophilic attack to occur through a relatively low energy transition state to give this intermediate. And and then electrons swing down and push out the chloride and give you the ketone. Once the ketone is formed, now there's enough sterics here and a smaller amount of charge involved. So bringing in another R group goes through a much higher energy transition state than the R group went through when it was brought in the first time around. And so there's really no significant reaction over a reasonable period of time between the Gilman reagent and a ketone. So this reaction stops at the ketone, and that's going to be the final product. Right? So you want to think about practicing the difference using a Grignard versus a Gilman reagent, and how the outcome of that reaction produces a ketone with the Gilman reagent versus going all the way to the alcohol if you use a Grignard. All right, so this slide here kind of summarizes some of the things that acid chlorides can do. Right, so we showed how with an alcohol and pyridine we can make an ester. With an ammonia, primary amine or secondary amine, we can make one of these amides. The LAH will make primary alcohol. This more sterically hindered lithium aluminum hydride reagent will only deliver one hydride, and so that will convert the acid chloride into an aldehyde. The Grignard will make a tertiary alcohol. The Gilman reagent will end up making a ketone. So that's kind of a lot. There's a lot of options there that the acid chloride can undergo. So you want to practice that, using that in a variety of reactions, so when you see it on an exam potentially next week, that it doesn't look too confusing to you. So let's look at a couple examples. So let's say I've got carboxylic acid. I want to make that into an acid chloride, right? So if you're not seeing those functional groups based on this condensed structural formula, this is what we're starting with, and this here is a CO Cl. So if I want to convert a carboxylic acid into an acid chloride, I use thionyl chloride and pyridine. We showed that mechanism. Once I have an acid chloride, there's tons of things I can do. There's just two options. So I want to maybe count these carbons. So what's happening is I'm bringing in 5 more carbons in the form of a ring to attack carbon 6. And so if I want that attack to occur and then avoid a second attack, I don't want to use the Grignard. Normally, what we've seen here is using, if I want to make a new carbon-carbon bond between 6 and this 5 carbon ring, I might put a magnesium on there and make that a Grignard and then have it attack carbon 6, push electrons up to the oxygen. But with the chloride there, they would swing back down and push out the chloride, and I would produce this product. But if I had a Grignard, then it would attack again and push electrons up again. So I want to avoid that. So I'm going to use the Gilman reagent. And so I just put 2 of those R groups on either side of a copper. And that will allow one to be delivered, but then the sterics associated with the product and the smaller amount of partial positive here will mean that the second one won't be delivered, and I'll be able to stop at the ketone. So that's the reagent that I need there. And I forgot to mention, this creates a negative, so there's a lithium there as well. I knew there was something missing. So then that would be this step here. If we want to go down here and make this product, what I'm seeing is a similar situation. I've got the same carbon skeleton, except here I want carbon 6 to bond to a nitrogen. So I need a nitrogen nucleophile. And in this case, I'm making an amide linkage. So this compound, the nitrogen would come into the carbon, push electrons up to the oxygen, they'd swim back down and push out the chloride. That would give me this, except there'd be a proton here. So I need 2 moles of this so that the second one can pick off that proton that would still be here and then leave you the lone pair that you have in the amide linkage. All right, so that's acid chlorides. Next, carboxylic acid derivative we want to focus on a little bit is the anhydride. And sometimes anhydrides are formed through a dehydration reaction at elevated temperatures, but this really is not a very practical reaction because the temperature is too high for most molecules, depending on, if I just have a methyl group here, this works okay, I get a decent yield, but if there's a more complicated R group with more carbons and hydrogens and other atoms potentially, this temperature is going to start breaking out. It's going to start decomposing. And so it's obviously not going to give me the product I want. So we're not really going to focus on that reaction. Rather, to make an anhydride, if that's your goal, you'd start with an acid chloride. And you treat that with a carboxylate. A carboxylate is a pretty weak nucleophile. Why is it weak? Normally a negative on an oxygen is pretty strong, but this one is stabilized through resonance, so it's really only half of a negative on each oxygen. It's not really that much negative, and so it's not really that unstable, right? So it starts relatively low in energy, but that's why we're using the acid chloride, because it has so much partial positive, and it's so unsterically hindered. It's relatively high in energy, so it doesn't take much energy to get this to collide. And it is still a full formal negative, so it's not extremely stable, even though it's stabilized by resonance. And so this oxygen can come in here and attack as a nucleophile, pushing electrons up to give this intermediate. When the electrons swing back down, it could push out the carboxylate and go back. Or it could push out the chloride leaving group, which gives you an anhydride. What's convenient about this approach is the R groups don't have to be identical, right? So the limitations over here where the high temperature start to decompose the R group, but what happens here is two of these have to come together and lose a water molecule and then connect. And so if two identical structures come together with the same R group, there's no way to avoid the product having the exact same R group on both sides of the anhydride. So I can't make an asymmetrical anhydride with different R groups attached. So this is a nice synthesis because this R group could be really any R group I want. And so could this one. I can't have any protic sites on the R group. You know, if I have an R group that consists of some chain and then there's like an OH on the end, that's not going to work because the OH would also be able to attack there. It's also a decent nucleophile. Right? So there's some limitations on what the R group could be. But as long as it's a hydrocarbon group, just carbon and hydrogen, it could be anything I want here and anything I want here, which means I can make an anhydride with different R groups on either end if I like. So if you need to make an anhydride, that would be the way to go. And when it comes to anhydrides, they're pretty similar to acid chlorides, mainly because they have a good leaving group like a chloride. Right? So if some nucleophile were to come in here, push these electrons up, well, those electrons would then swing back down and push out the chloride, and we know chloride's very good at stabilizing a negative, and that negative would form readily, and that would mean that the nucleophile could replace the chloride. We saw lots of examples of that today. The same thing could happen here. Push the electrons up, they'd swing back down and push out this leaving group. And that leaving group would have a negative on an oxygen. So is it more stable to have a negative on a chloride or on an oxygen if the oxygen is stabilized by a resonance? How do we judge the stability of a negative charge? Well, we use our convenient Scario acronym. And so assuming these are in the same solvent, that wouldn't really help us distinguish. They have the same quantity of charge. They're both -1. And so the next factor is the atom, right? So generally, if the atom holding the charge is significantly larger and more able to stabilize a negative than another atom, then we really don't have to worry about the resonance because it's not as major of a factor as the atom holding the charge is. So, which is a better leaving group? The chloride. Why? Because the atom is much larger. It's a larger atom, it stabilizes a negative charge better by spreading that negative charge out over a larger space and avoiding as much of a charge imbalance in the charge ratio on the atom. But the acetate, or I should say carboxylate leaving group here is also pretty stable with the negative spread out through resonance on two oxygens. So this undergoes a lot of the same reactions that the acid chloride undergoes. And the advantage here is this structure isn't quite as reactive. Right, so let's take a quick look at that. So both of these have their own advantages and should be used when appropriate. The chloride is such a great leaving group, almost any nucleophile can come in here. And that's nice because it gives us a lot of flexibility in whatever nucleophile we want to use to come in and replace the chloride. The chloride is, through induction, pulling electrons away, and the resonance is minimal, so that creates a very large partial positive here. Over here, the oxygen being connected to the carbonyl-carbon rather than the chloride, the oxygen can donate some electrons through resonance. And so when this oxygen swings its electrons up to create a positive on the carbon, this oxygen can swing electrons in to alleviate some of the positive on that carbon. So the quantity of positive that this carbon holds is not as much. Which means if we looked at their relative energies, the acid chloride is going to start off higher in energy than the anhydride. So almost any nucleophile can come in here and attack. Even if the nucleophile is relatively stable and it attacks to produce a relatively unstable transition state, that transition state won't be much higher than the acid chloride because the acid chloride already starts higher in energy. Oops, I should have shown that there. So the activation energy isn't that high and that reaction can go pretty readily. With the anhydride though, the weaker nucleophiles don't really react effectively with it, like for example water. With enough time, this could react. But in a reasonably short time period, for water to come in here and push electrons up, since the anhydride is lower in energy than the acid chloride to begin with, to get from there up to the transition state and form the intermediate, it's actually even probably a little higher in energy because the intermediates can have a little bit more steric hindrance with these R groups and stuff. That means that now I'm looking at a much higher energy, activation energy. So the advantage of the anhydride is it's not as reactive. Well, why is that an advantage? Wouldn't I want it to always be more reactive and make the reaction more likely to occur? Well, the advantage to having a less reactive reactant is that it's easier to store. And I don't have to worry about water reacting with it immediately upon contact. Right? So that's the disadvantage here. If I want to store this, I have to store it in a dry atmosphere. Can't have moisture come in because the water will come in and replace the chloride, as we showed earlier. The anhydride I can keep on the shelf for a while. If a little moisture gets in, it won't react in it very quickly. I can put water in the reaction. I don't have to worry about the water immediately reacting there. So this is a nice alternative for if I have a weak nucleophile around that I don't want to attack, and it's in competition with a stronger nucleophile, I still have a good leaving group, so the strong nucleophile could come in, push electrons up, they'd swing back down out and push that leaving group out. But the weak nucleophile wouldn't be so reactive. Right? So in organic chemistry, you're probably noticing we like to have lots of different options, and every option is slightly different from the other, so that we can pick out whatever compound or reaction is optimal for our situation. So because anhydrides have a great leaving group, any of these nucleophiles can react with it given enough time, especially the stronger ones. Even water can react. It's a slower process. So typically you might add a catalyst or something to speed that up. But the acid anhydride can be converted back to a carboxylic acid, and it can be converted into most of these products. And some of you have been doing a reaction between this and this in your lab 4. This methoxy group pushes electrons in, and then from the para position it can attack this acid chloride. Because there's a good leaving group, you end up with this acyl group connected to the ring. There's a Lewis acid catalyst to facilitate that, which caused an explosion, unfortunately. So we won't be doing that reaction anymore in our labs, but that does work if you're very careful with it. Some other groups, we're looking at this in lab 4. They used aniline. And since this aniline is reactive toward acid, they wanted to do a nitro reaction, add a nitro group, but under the acidic conditions, that would protonate the nitrogen. So they had to first react it with acetic anhydride. And the nitrogen coming in there, pushing electrons up, swinging back down, pushing out the leaving group, allowed that R group there to produce the acid acetanilide compound from the aniline that they started with. Right? So we've already worked with this in lab, and now we're seeing a little bit more detail how and why it works. Another advantage to working with anhydrides is we don't need purity. Why don't we need purity? Because the leaving group acts as a base. And so earlier we were saying, so I'll just put here, we were saying that when we have an acid chloride and we use some nucleophile, maybe an alcohol or a water or even an amine, once the nucleophile attacks and then the leaving group leaves, oops, should be an oxygen. The leaving group leaves. It got this proton that needs to be picked off, and that's why we used pyridine. The advantage of the anhydride is we don't need to add that. So if I do the same process, but I start with an anhydride instead of an acid chloride, and I want to attack that with some kind of weak nucleophile, I still end up with this proton here that needs to be removed. But when the leaving group is a chloride, the chloride is such a weak base it can't remove it, which is why we needed purity. Well, it can, but not very readily. So when this lone pair swings in and pushes out this leaving group, the carboxylate that results is basic enough, the leaving group itself, even though it's stabilized through resonance, is basic enough to remove that proton. So the anhydride has a nice built-in base that forms when the leaving group leaves, because the leaving group itself is a weak base. So the answer there is the leaving group is a weak base, and so it takes the place of the pyridine, which we don't need to add. And that means there'll be a carboxylic acid byproduct, which is a disadvantage, right? So it's nice to have this here because when it picks off the proton, it stabilizes the product. This would be our desired product, where we're trying to use this to make an ester maybe. But when the leaving group picks up a proton, it produces a byproduct. That would be the carboxylic acid that produces when this negative charge picks up that proton. And that's a disadvantage because then we have to remove that. So depending on the specifics of our compounds, that might be removed in a variety of different ways. One way to remove it is to add base. And those of you who did the reaction with an anhydride in lab, if you recall, probably that reaction during workup required you to add some kind of weak base. And so some kind of base like a hydroxide or even a carbonate or something, pick off that proton, that would convert during the stage where you're using a separatory funnel and you have two different layers. Adding a base to the aqueous layer would pick off that proton and convert the byproduct I'm trying to remove into a charged species that would then be more soluble in the aqueous layer and it would be removed from the product. So the product would be in the low polarity like tert-butyl methyl ether layer, and the byproduct, which would be protonated when it picks up proton here, would be deprotonated by some kind of base to produce the carboxylate, which would be charged and then end up in the aqueous layer. So here's just two examples of that, right? I use the anhydride to convert this into an ester. I use an anhydride to convert this into an amide. And here are two practical examples of that, right? So you can take salicylic acid and convert it into acetyl salicylic acid, which is also known as aspirin. That makes it a painkiller. This is the reaction where you would do that. You'd use acetic anhydride. You could also use acetic chloride with a chloride group here, but then you have to worry about excluding moisture and storing that. It's more expensive, so this may be a more practical option. You can also take this, which is 4-hydroxyaniline, and do the same reaction. The nitrogen is a stronger nucleophile than the oxygen, so it would be the one that attacks, push electrons up, they swing back down, push out the leaving group, then the leaving group would pick off that proton, and you get Tylenol, which is obviously another painkiller. So these are practical reactions. All right, so we've talked about acid chlorides a little today, we talked about anhydrides a little. Now we'll talk about esters, which are another very common functional group that can be derived from a carboxylic acid. And this is typically formed by combining a carboxylic acid with an alcohol. So there's really two ways to make an ester. This option here is option one that uses an acid catalyst. The second option we'll see in a minute, and we've actually already seen, is to go through an acid chloride. It's nice to have options in case you try one reaction, it doesn't work, try the other, and then you can still make the product that you want. So option one, acid catalyst. Obviously we're going to add maybe some small amount of sulfuric acid or something. It's a catalyst, so it'll be regenerated. And in the mechanism, the acid would protonate, probably the alcohol, more likely to end up protonating the carbonyl carbon, right? So this oxygen here can't stabilize its positive through resonance. So this lone pair would pick off that proton because now the pi electrons can shift up there and stabilize the positive over both the carbon and the oxygen through resonance. The point of the acid catalyst is to make this a better electrophile. And if we had an acid chloride, we wouldn't need that because the acid chloride is already very electrophilic. But the oxygen here can donate electrons in through resonance to stabilize that positive, so it's not nearly as reactive. It starts off lower in energy, so we need to add the acid to protonate it and make it much less stable, giving it a form of positive, so it'll start higher in energy. Then the nucleophilic attack won't have to go through such a high activation energy to get to its transition state. So now this is very electrophilic, even more electrophilic than an acid chloride because of the positive charge attracting the partial negative there, and the fact that the positive charge attracts these electrons up, making this positive through both induction and resonance, making this a much bigger partial positive to attract that negative. So the nucleophile can then attack, push electrons up here. Now I've got a positive on this oxygen, which becomes this one, because now it has 3 bonds after it attacks, and so it would be deprotonated. And what we see very often in these acid catalyzed reactions is that protons just kind of shuttle back and forth kind of randomly. All these steps are equilibrium, and when this oxygen picks off that proton, then this oxygen could just pick it right back. And so they go back and forth. Eventually, if this oxygen picks it up, though, and the electrons stay back here, I get a species that is neutral right here. But there's not very much entropy here because I've combined 2 molecules into one. There's a fair amount of sterics, all this stuff cluttered around. So if once in a while one of these 2 OH groups picks up a proton, becoming a water-leaving group, the other one can shift electrons in and push that out. And then picking off that proton to regenerate the catalyst, swinging electrons in can form the ester product. So you should be able to get through this mechanism. It's called Fischer esterification mechanism. It is in equilibrium. We need the acid to protonate things and get through the transition state more readily. And when we have acidic conditions, we should avoid negatively charged intermediates. So in this mechanism, the acid catalyst is there for kinetic reasons, right? Otherwise, without that, to get this weak nucleophile to attack this relatively weak electrophile, they're both relatively weak, they're both relatively low in energy. To get that to attack directly and create an intermediate with 2 formal charges, it wouldn't happen very often. So the acid catalyst is there to protonate this, give it a positive charge, make it a better electrophile, make it much higher in energy, so the slow step of the process can happen more often because we've started with a higher energy prior to that point and not as much energy is needed to get to the transition state. So this is for kinetics. We also want to look at the thermodynamics. Thermodynamics is about comparing the initial reactants to the final products. The mechanism is irrelevant. All that matters is how stable are the reactants versus the products and how much entropy is there in the reactants versus the products. So when we look at whether or not a process favors the reactants or the products, we want to look at the enthalpy term, we want to look at the entropy term, and try to predict the sign for delta G. So the entropy term is going to be pretty close to 0. Because we've got 2 moles of reactants, 2 moles of products, there's going to be basically the same amount of variety, positioning, and motion for particles on both sides of that equilibrium. If we want to look at the stability term, the enthalpy term, they all also both look pretty stable, right? There's no formal charge on either side, there's no strong acid or base on either side. Everything looks pretty stable on both sides. So this also will be pretty close to 0. So this is a situation where we kind of have a true equilibrium where it could favor either side. And so if we want to shift it to one side or the other, we have to use Le Chatelet's principle to do that. So if I want to shift it toward the products, I use excess reactant. Whatever the alcohol is that I'm trying to connect here through to make an ester, I use excess of that. I would use it as my solvent. I would have a big excess of it. If I wanted to shift it back toward the reactant side, I use excess water. I would use water as my solvent. And unfortunately, there's no entropy difference to be exploited, so I can't even use temperature to help me either, right? If I had a value for delta S that was something more than 0, depending on whether it's positive or negative, I could increase or decrease the temperature to make this term larger or smaller and affect the value for delta G and shift the equilibrium one way or the other. But when the T delta S term is very close to 0, no matter how I change the temperature, the term is still going to be very close to zero, which means the temperature change is not really going to affect this equilibrium much. Keep in mind though, since this can go both ways, acid, catalyzed, alcohol, and carboxylic acid can form an ester. But if I want to return the ester to the carboxylic acid, then I just use excess water, also with an acid catalyst. So we were saying, where was it? Oh, I got rid of it. Oh, we were saying on this slide, we were saying there's two ways to make an ester. One is with an acid catalyst, and two with an alcohol and pyridine from an acid chloride. All right, we already talked about that a little bit, but here's another generic example of that. So if I'm able to make an acid chloride and protect that from water attacking it, the chloride is a great leaving group. And so in this case, I don't need an acid to make this a better electrophile. The chloride and oxygen are already pulling electrons away through both resonance on the oxygen and induction on both so strongly to create so much of a partial positive that the oxygen can readily attack there. And as we were showing earlier, oops, do that again. The intermediate would have two formal charges. So very quickly, it's pretty unstable with those, so very quickly push out the leaving group. So that produces the ester almost, but it's protonated. And so that's the purpose of the pyridine. Pyridine would pick off that proton and make the product. So I would also form pyridinium. But that's relatively stable. And you'd also get a chloride. So those two being charged would be easily removed in the aqueous layer, whereas the low polarity R groups would allow that to exist more in the low polarity ether layer. So I could separate that byproduct. So that's the alternative. So you got two routes, and you got two options for success with that esterification reaction. So that's two ways to make esters. And what kinds of reactions do esters undergo? So I can make an ester using an acid catalyzed Fischer esterification, or converting a carboxylic acid into an acid chloride and adding an alcohol with pyridine. If I want to react an ester, the main reaction esters undergo that we haven't seen yet is a hydrolysis reaction. So there are two ways to hydrolyze an ester. One is here. If I have an ester and I use water, the word hydrolysis breaks down to water or hydrolysis or breaking. So I'm breaking the ester with water. So if I use an acid catalyst and large excess of water, I can do a hydrolysis reaction, which converts the ester back into a carboxylic acid. So that's one way to do a hydrolysis, which we already discussed. The other option is to do a hydrolysis in the presence of a base. This is called saponification because it's used to make soap, which we'll talk about in a minute. But generally what happens in a saponification or base-promoted hydrolysis reaction is you've got an ester and you treat that with aqueous hydroxide. And so the hydroxide is a pretty strong nucleophile. So we don't need to protonate this first, and if we did try to protonate it, the hydroxide would just pick off the proton. So it'd be pointless to try to do that. So instead, the strong base, the hydroxide, will attack here, push electrons up to make this intermediate. Then when the electrons swing back in, it'll push out this leaving group. So why would it push out this leaving group instead of the hydroxide? Because if the electrons swing in and push out the hydroxide, it could go back. In this case, though, the OR is a better leaving group than the OH, mainly because of sterics. Right? The OR and the other R, and the OH, everything in here is a little bit crowded. So if the electrons swing in and the OR group leaves, that will alleviate some of that sterics. And so that would produce this. If the electrons swung in and pushed the OH group, I would just go back. So that could also happen. But eventually the OR group would also get pushed out. And at that point, the last step of the mechanism is not reversible. Right? So once this OR group gets pushed out, it's not going to come back into the carbonyl carbon. There's not enough partial positive there to attract it, and there's a lot more partial positive on this proton due to the electronegativity difference here. So what's going to happen is the negative on this oxygen that has a big bulky R group that won't be well solvated and will be pretty unstable is going to pick off this proton to produce our carboxylate. So the negative stabilized through resonance, and this oxygen pick off that proton. It's going to produce something that's way more stable, right? So this negative stabilized through resonance is never going to go back to this other negative here. So this step is pretty much irreversible. Once that occurs, that's your product. That's what you end up with. If you want to make this into a carboxylic acid, you need some H3O plus in a second step. It must be added at the end in a second step. So the OR would pick up that proton because the negative would be way more stabilized through resonance than over here on the OR. And then if you want to make this into a carboxylic acid, after you allow for this whole thing to react forward and for this species to accumulate in solution, when you believe that has occurred fully, then you would add H3O plus. And this would be forced to pick up a proton to give you the carboxylic acid and this alcohol. So the hydrolysis of an ester produces a carboxylic acid and an alcohol. It's the opposite of the formation of an ester, or esterification from a carboxylic acid and an alcohol. Except for here we're doing it under basic conditions rather than using an acid catalyst. It's a very common way to hydrolyze an ester. So common, in fact, that it's used to make soap. So actually, let's talk about that real quick, and then we'll come back to the quiz question. So we were saying hydrolysis of an ester is in equilibrium. Depending on the conditions you use, that can affect that equilibrium. So let's just go back here quickly and mention about the difference between the two methods of hydrolyzing an ester. This method of converting the ester into the carboxylic acid, its equilibrium is tricky because neither of these factors really help favor one side or the other, and we have to really rely exclusively on, for the most part, Le Chatelier's principle to shift it back and forth. And so that's a situation where maybe it's hard to get the equilibrium to really fully favor one side. So if I have this ester and I want to break it apart, using an acid catalyst in water, the more excess water I use, the more it'll break apart, but I still might not be able to get the equilibrium to really favor the products. So this is probably not your first method of choice because equilibrium isn't super easy to control. Over here, when I use a base to hydrolyze an ester, this is usually a more reliable option, specifically because this step here is not really reversible. So the first step can shift back and forth. Once the OR leaving group gets pushed out, though, it really won't go back, because instead of attacking the carbonyl, as we said, it would pick off the proton and go forward. So this would really accumulate. This equilibrium really greatly favors the product side, because the negative stabilized through resonance is way more stable than the initial negative on the reactant side. If we're looking at the equilibrium, comparing the stability of the reactants versus the products are way more stable here. And then we can protonate that by adding H3O plus. So this reaction probably a lot more reliable to forming the products. So in the case of this is a little too generic, so let's make this a little more specific. So instead of talking about this, let's say, that was really sloppy, gotta be a little more careful with that. So instead of this, let's say we're looking at saponification with OH minus specifically. That one already favors the products dramatically due to the stability of the negative charge when it's stabilized by resonance on the product side versus not being stabilized by resonance on the reactant side. So we don't really even need to use Le Chalet's principle to favor the products. We could use excess OH minus. That would help. Oops, extra electron there. The excess OH minus would help shift it toward the product side. And if you want to shift it back to the reactant side, you really can't. So I'm not going to be able to use OH minus to make an acid carboxylic acid back into an ester. It's just not going to happen. And it's not because of entropy, it's because of the stability of the negative charge. So this is how soap is made. So if we're looking at making soap, we're looking at starting with a triglyceride, which is found in usually animal or vegetable fat. And a triglyceride looks like this. It has glycerol, which normally have OHs here. But the glycerol is connected through ester linkages to these long alkyl chains. So we'd have one there and one here. And just to point out what those look like, they would just be, long, probably somewhere between 18 and 25 carbons. They may have pi bonds, they may be trans or cis, or they could just be a straight alkyl chain. There could also be some branching, usually not though. So what happens is we use the conditions we just talked about, OH minus and water. And if you've ever seen the movie Fight Club, you know the scene where they are making soap and they use lye, which is hydroxide, to react the fat that they've gathered through illicit means to make this high-end soap. And they're basically doing this reaction. The hydroxide attacks the carbonyl carbon, electrons swing up, and when they swing back down, it pushes out this group. So what that produces initially is the hydroxide now is connected to the CO double bond, and the R group is still there, the long chain. And then when the glycerol oxygen leaves, so this one hasn't reacted yet. So those chains are still there. But when this leaving group leaves and you get a negative charge, it then picks off that proton. And so this oxygen gets protonated, but the key thing is the soap, right? The soap is this carboxylate. If you make a carboxylate with a long carbon chain and a negative charge here, that is a surfactant. If you remember from Gen Chem 2 and from OChem 1, we talked about surfactants a little. We said since there's a charged end and a non-polar tail, these things will aggregate together into micelles. I didn't draw that well. So the negative charge will exist on the outside where it can attract to polar water molecules, and the tails all point toward the center. So there'd be negative, negative charges all the way around the outside here. And that is so because any oil or grease that's low polar and won't really readily dissolve in water will readily get pushed in the inside of this micelle and washed away. All right, so let's go back here and look at the quiz question. So I was looking at your answers this week, leading up to today for your quiz questions, and I wasn't really even thinking fully about the question. I was just looking for what reagents can be used to make this product, and there's a few different routes you can go through. But earlier today, when I looked more closely at the question, it does specify that all the carbon atoms in the product should come from a molecule of the reactant. So that means this reactant is going to have to be formed into a couple different things that then react together to produce the product. So what can we do with this reactant? Well, what we see here is a cyclic acetal. Here we have this ring, which makes it cyclic, and the acetal means there are two oxygens both bonded to the same carbon. So what we're going to do here first is to treat this with H3O plus and water. That's really the only, the only reaction we've seen that acetals undergo. And the H3O plus and water will revert the acetal back to the ketone, in this case, or aldehyde in other cases, that was used to form the acetal, and it will produce the diol. And so this is reversible. If I use excess of the diol, I'll form the acetal. If I use excess water, due to the Lachau's principle, I'll shift it back and form the ketone. So instead of using excess diol, I use excess water, and I can get this ketone. So when I'm looking at, I'm working forward from the cyclic acetal because there's only one reaction we talked about that those will undergo. So there's really no other option there. So then maybe I also want to look at the product and kind of work backwards. Right, so this is probably just a byproduct that would be removed, but basically I'm forming acetone here from this cyclic acetal. So how can I get acetone into this product? Well, what I'm noticing is there are 3 carbons here, and there are 3 carbons here. So I can make acetone into this part of the structure, and then somehow I've got to make acetone into this part of the structure. So what can I do with this acetone? So I'm going to use H3O plus and water here to make the acetone. And I'm not going to show this because that's just a byproduct. So once I've got the acetone, there's a hydrogen here, and there's no hydrogen here. And so counting the carbons and looking for the hydrogens in the areas where the reaction is going to occur is really going to help me know what to do here. And so what I would do with this acetone is to use LAH and then H3O plus. And that would deliver a hydride to that carbon to put the hydrogen there that I need there in the end. That would make that into isopropanol. So this oxygen can be this oxygen. So now I just have to take this proton off and get this oxygen to connect to this carbon. So what I also have to do then is to think about how can this acetone be made into this part of the structure. There's a few different ways to do that, but right now I don't have any leaving groups, and I need to get one of these carbons out of here because this part of the structure only has 2 carbons. So probably one way to do that would be to use a peroxy acid. That would promote the Baeyer-Villiger reaction we talked about recently, and that would insert an oxygen between the carbonyl and one of those methyls. Now I've got an ester, and I can use the hydrolysis reaction we just talked about. So the point of this is to separate one of the methyl groups from the carbonyl so I can get rid of it. And I can get rid of it through the reaction we just talked about, which is the hydrolysis of an ester. So I use hydroxide and water. And that would break apart the ester to make carboxylic acid. Assuming I add H3O plus in a second step to put that proton on there. Now that I have a carboxylic acid, I can use thionyl chloride and pyridine to make it into an acid chloride. And so that's the key. Now I've got a leaving group, got an acid chloride with a great leaving group, and I've got a weak nucleophile in the form of an alcohol, so the alcohol can attack here, push the leaving group out. I would just need a little pyridine to pick off that proton, and that would give me the product. So there's probably other ways to do that, and if in your answer to the quiz question you use some other reagent that involved carbons that didn't specifically come from the original reactant, I won't take off for that. I would have commented on that if I had noticed that was an issue before. But this is technically probably the best solution given the way the question is worded, where it asks you to form the product only from carbons that start from this reaction and go through the acetone intermediate. So this is just, I wrote that up to just kind of show that process, right? So we form this acetone from the cyclic acetal. We can make acetone into an alcohol. We can make acetone into an acid chloride. And those two can be reacted with pyridine to make the ester. All right. I'm going to skip this because we did already talk about that. And I'm also going to skip this one because it's not a very practical reaction. If you want to make an amide, doing it from an ester is not your best bet. It'd be much smarter to start with an acid chloride or even an anhydride, because either of those have a better leaving group than the methoxy leaving group. So if I use 2 moles of that, it would come in here, push electrons up, they'd swing back down, push out the chloride. The second mole would deprotonate the nitrogen, so you'd only have 2 protons there, and that would give you the amide. It says right on here, this reaction that was originally on the slide isn't very useful. All right, so what else can esters do? Esters can react with LAH. We've seen this reaction earlier in the semester when we talked about using LAH. So we know that the aluminum, the LAH, deliver a hydride here, push these electrons up. And the methoxy group is a better leaving group, or more stable with the negative than the negative on the aluminum or the hydrogen. So this will swing in and push that out. That will give me an aldehyde initially. And the OMe will be more stable than anything else, so it'll accumulate. But then we have excess, so another hydride will be delivered. Now there are 2 hydrogens here, and that will accumulate, both of those will accumulate until water, and usually H3O plus accompanying it, will protonate those oxygens to give you the products. So an ester will be cleaved if you use excess LAH, and both this carbon and obviously this will end up bonded to OH groups. So here's a variation on that. It's very similar to one we were talking about earlier. Earlier we were talking about how if you use acid chloride, you can use this hydride reagent with the terp-butyl groups. And that will only deliver one hydrogen, and you'll end up getting an aldehyde, because once it delivers one, it sticks around and creates too much steric for another hydride to come in and reduce that all the way down to the alcohol. So here we're using a reagent called diisobutyl aluminum hydride. And so we've got two isobutyl groups on the aluminum hydride. And this is typically used if you have an ester. Right? So if we use lithium aluminum hydride, the ester will be converted all the way down to the primary alcohol. It goes through an aldehyde intermediate, but once the aldehyde forms, you can't prevent another aluminum hydride from being delivered to further reduce it. So the point of the diibol is very similar to this compound. It's got these big bulky groups, these isobutyl groups, attached directly to the aluminum. So when this one delivers a hydride here, pushing the electrons up, they'll swing back down and push out the OMe. That single hydride will be here now. And now that the aluminum only has these two bulky isobutyl groups and a fair amount of positive charge, it will attract nicely to the oxygen, and it will stick around. And it will be bulky enough, and this one will be bulky enough, where it won't be able to deliver another hydride into the carbonyl and further reduce it. So you can form an acid chloride into an aldehyde using this bulky aluminum hydride reagent, and you can usually form an ester into an aldehyde using this other bulky aluminum hydride reagent. If you get the bulky aluminum hydride reagents confused, that's okay. If you use either one of them, I'll give you credit, because the point is that you understand the concept and the need for one or other of those reagents, and can recognize when a bulky aluminum hydride reagent is necessary. We've already seen this before. We know esters can also react with Grignard reagents. So the Grignard obviously has an R group bonded to magnesium, and it pulls the electrons away and delivers those electrons. Right? So we come in here, push electrons up, they swing back down, push out the leaving group. And again, we can't control the Grignard. It's too reactive. So another Grignard would come in, and then that would accumulate in solution until a second step where H2O plus and water are added to pronate that and give you alcohol. So that's again a way to form a tertiary alcohol with two identical groups. So this is basically the same reaction we saw earlier. Whether I have a chloride leaving group or an alkoxide leaving group, any decent leaving group that can stabilize a negative when it leaves, better than the R group can stabilize a negative, any decent leaving group that can even remotely stabilize a negative would leave here to produce a ketone, and then another Grignard would attack, and you would eventually get a tertiary alcohol. So there's a couple different ways to make tertiary alcohols using these reactions. All right, so let's take a look at this example here. Looks kind of complicated. What I'm seeing here are two ester linkages. And what I can see going from this reactant to the either set of products is that obviously the ring is opening up. I don't have a ring in my products. And in each reaction, I'm forming two products instead of one. So that suggests that both these ester linkages have to break. But I want to count the carbons and be real careful so I know exactly what reagents I need to use here. So in the reactant, I've got 1, 2, 3, 4, 5, 6 carbons, and I've got 7, I've got 8 total. So if I'm looking at this set of products over here on the right, what I can see is got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Same number of carbons. So what has to happen here is there has to be a lot of hydrogens delivered. And so if I'm looking at carbon 1, there are no hydrogens. Later, there's 2 hydrogens. When I'm looking around here at carbon 5, there's 1 hydrogen, and that's still there, so I don't have to worry about delivering a hydrogen there. On carbon 6, there are a couple hydrogens, and those are still there. On carbon 7, there's no hydrogens, but over here, there are 2 hydrogens. So I have to deliver 4 total hydrogens to the carbonyl carbons. So how would I do that? Well, I would use LAH. Just using LAH through the reactions we just saw moments ago, the hydride would be delivered here, push electrons up, they'd swing back down and push out this oxygen, and that would break the bond between carbon 7 and this oxygen that's on carbon 5. But when the electrons swing back in to reform the double bond here, another hydride would be delivered, and that's how I get 2 on that carbon. And then this would be a negatively charged oxygen until it's protonated by the H3O+. So I would really need 4 equivalents of hydride, because I have to deliver 4 hydrides. 2 to this carbonyl carbon, and 2 to the other carbonyl carbon. One would come in here, push these electrons up, and when they swing back down, it would push out this leaving group. That's how the ring gets open. That's how this oxygen here, that's on carbon 6, gets separated from carbon 1. Then a second hydride would come in, push electrons up, and so that's how this oxygen would become negative and how I get 2 hydrogens on carbon 1 instead of 0. And then this would be protonated after the H3O+ is added in the second step. And now I'm noticing an error on this slide. Oh no, it's fine, okay. So, what's happening over here? Well, we got the same basic carbons. But we've got additional carbons. We've got 1, 2, 3, 4 methyl groups. So I'm adding these methyl groups. So what I would be adding then is methyl magnesium bromide. Adding the methyl groups as a Grignard reagent will allow them to come in. And I need 4 of those. So similar to the hydride, the methyl group would first come in maybe to carbon 7, since it's probably less sterically hindered, push electrons up, they'd swing back down and push out this leaving group. So that breaks it into 2 structures. Then another methyl would come in and push the electrons back up, and they would stay up there until a second step where H3O+ and water is added to protonate that oxygen. And so basically I'm delivering methyl groups through a Grignard reaction instead of hydrogens through a hydride reagent. Then obviously the methyl groups would attack carbon 1 as well, would come in, push electrons up. Since it's an ester, they'd swing back down and push out the leaving group. And that again would break this oxygen that's on carbon 6 away from carbon 1. Delivering a second methyl group to carbon 1 puts 2 of them on there. That would shift electrons up, and I would get a negative here until it's protonated with the H3O+ in the second step. All right, so that's more stuffs for y'all to practice. And let me know if you have any questions about any of that. Can't believe it's already Wednesday. So here are the relevant videos and sections to read for this coming Monday, which is day 23, and make sure you get the quiz questions for those looked at before Monday. In the meantime, let me know anytime you have any questions.